Hey everyone, welcome to GoWayFest. I'm El, and I'm here to present you this talk, The Quest for the Fastest Deployment Time. So that's the name of the talk, that's my name, that's the name of my company. Okay, so my company, Tilt, we are a company focused on development experience or creating development workflows. And there are many metrics that we like to keep our eyes on. So for example, if a developer is having to type too many commands whenever they make a change to their code, we don't want that. We prefer to automate everything. There are many things like that, but the most important metric is the feedback loop time. So how long does it take? And that is the main question that this talk is about. How long does it take between you making a code change on some file you're working on, you make a code change, you save the file, how long does it take for that change to be live and running on your development cluster? And that is the question that we're going to be discussing today. We want that time to be as small as possible. Now, I posted this question on Twitter late last year. And so how long does it take between changing a line of code and that code running in your development cluster? And most people answer 30 minutes. So they're probably doing CI in development, and I'm going to complain about this in a second. But like 30 minutes, to me, that's not acceptable. In 30 minutes, you completely forgot what you're doing. You lost your train of thought. By the time you're back to working on it again, you kind of wasted a lot of mental cycles there. 1 minute is okay. 1 minute can be fine. Depending on what you're doing, you're not going to be able to do better than that anyway. But 1 minute is enough time to pick up your phone, to check Twitter, to, I don't know, look at pictures of cats or whatever, and you also get distracted, and that's not healthy when you're in a creative flow. And the least amount of people said 2 seconds, and if you're watching this talk and you watch it until the end, you're going to be in the 2-second frame, because we're going to take a feedback loop that is not ideal, and we're going to take it down to less than 2 seconds. So that's what we're going to do today. Now, we're going to have to follow 3 rules, basically. One is don't rely on CI for development feedback. And what is my point? So CI is important. CI has its place. I'm not saying never use CI, but my point is, so there is a time when you're creating a solution to a problem, like, okay, this program needs to do this. I don't know how to do it. I need to figure out, is this approach better? Is that approach better? I'm going to try this, let's see, and then I'm going to try that, and then I'm going to try the other thing. When you're doing that, when you're in this process, your feedback loop should be as small as possible. You should not have any distractions. You should not pick up your phone while you're working on that. Ideally, you're going to have tooling that does an instant refresh for you, so that you can be exclusively focused on what you're trying to do. Once you have a solution, once you've created something there, you have something that, okay, I think this is a good candidate for this, then you create a PR, then you push it, and then CI runs. So that's my rant about CI. You don't want CI running every time when you're trying to quickly iterate over ideas. Next rule, you need to use an MDX tool. So if your developers, if the developers on your team or you yourself, if you're typing Docker build, Docker push, kubectl apply, every time you make a change, you're doing it wrong. You should not be typing things by hand every time you want to try something. That just makes no sense. We have tooling to automate this, and some of this tooling, I created this acronym called MDX, so it stands for Multi-Service Development Experience. And then you can have MDX tools, MDX frameworks, etc. Some of those are Tilt, which is the company I work for and what you're going to see in this talk. There's Scaffold, was created by Google. A lot of people know about it. Telepresence was probably one of the first ones, so that's interesting as well, but it works a bit differently. And there's Garden. It's a company I used to work at, which is also very competent at this. My point is, I'm not going to hard sell you and say, hey, you need to use the tool of my company. I'm just going to say you should use some tool in this category, because you don't want to be typing a bunch of stuff by hand. Rule number 3 is use every hack, cheat, and dirty trick in the book. And we are absolutely going to do that in the next few minutes. And the goal of this talk, of course, is to achieve the shortest possible feedback loop. So that's what we're going to do. Now, how are we going to do this? We're going to have a Go app. It's going to be running on Kubernetes. I'm going to benchmark it always in parallel. I'm going to do it on my laptop running a micro K8s cluster and I'm going to compare that with running on Google Cloud, on GCP, on managed Kubernetes. So we're going to have both benchmarks for you to see every time. I'm going to use Tilt, like I said, because that is the tool that I'm most closely acquainted with. And our benchmarks are not going to be playing around. So lots of people, they try to do these things and they're like, oh, this fused faster, that was a bit smoother, blah, blah, blah. No. Here we're going to do down to the microsecond what's faster than what. This is the repo where you can check out the project we're going to use. Some of the screen caps that I'm going to show you here, the video captures are a bit old, so it doesn't look as pretty. It's a lot prettier now. So you can check it out there if you want to see. And here's what the application does. It's an image filter, and that before was a red filter. Now I'm going to create a glitching effect, which you can see here. And lastly, we have a machine learning thing that can, it's going to put some squares around the objects it detects. And it takes a bit to run because it's very not optimized. And then if you squint very closely, you can see that the one on the left says person, and that's a baby that's sitting there. The one on the right says teddy bear, and that is actually a teddy bear that's sitting there. In the original image, I mean, because like this, it just looks like rubbish. Okay, so what does Tilt do? Tilt watches your code for changes. So you have a project you're working on. Every time you change some file, Tilt's going to notice that you changed the file. It's going to rebuild and redeploy that service. Rebuild and redeploy, let's use those as flexible terms because sometimes it's not going to have to do all of that. And we're only going to use the glitch service. So you saw before there was a red service, glitch service, the machine learning, something. We're just going to focus on the glitch service. So this talk's not a Tilt tutorial, just want to make that clear. If you want to learn more about Tilt, you can message me later or visit tilt.dev. I'm just using Tilt to show you the Go and Kubernetes concepts that we need to work on. So let's get started. I'm going to have a Go Alpine image to start. This is basically the simplest thing that I think most people start with because they just don't know where to improve. I'm copying a bunch of stuff into my image. Then I'm going to build my executable inside the image, and I'm going to run that artifact, and that's what my image does. On the Tilt side, you can see the first 3 lines there are Docker build. So I have a glitch service, which is the only one we're actually going to be using for these benchmarks. So I have a glitch service. It has a Docker file called glitch.dockerfile, and it's only monitoring my glitch directory, my render API, and my Go mod file. When we look down a little bit, there's a KTML call. That's where I declare my Kubernetes manifests. And the last line, local resource something that looks complicated. Let's look into that. So here's how I'm going to do the benchmarks. I'm going to have a button on my interface that's going to say update. And every time I click that, it's going to change something in my code. What it's going to change in my code to simulate the code change, it's going to change that big number that you can see right here. So I'm going to click update. It's going to take that number, and that's a timestamp. And it's going to update the timestamp with the exact current time. So I click a button, and it's going to put inside my code the exact time when I click the button. Okay. Now, this code is going to be put inside an image. It's going to be compiled, and it's going to run inside my cluster. When it runs, it's going to get the current time when it's running. So we're going to have the time when I said update. We're going to have the time when it's running. We're going to do the subtraction. And then we're going to know exactly how long it took for the code to go from code change to code running. We're going to know that down to the millisecond. Okay, so now let's run it, the most basic version, and see what's happening. So now it's going to do everything, and let me give you a tour of Tilt. So this is the Tilt dashboard. These are my services. So there's a Tilt file, which just reads my Tilt config. I have a glitch service, a storage service, a muxer service, which is like the front end and the routing all in one, and update. This is the button that I click every time I want to do a separate test. And as we can see with this default setup, it took 28 seconds. Okay, 28 seconds is not terrible. And we're already automating a bunch of things. So we don't need to type a bunch of commands by hand, no docker build, docker push, we don't need none of that. Tilt's doing all of that for us, but 28 seconds is not perfect, so let's improve it. I did 3 measurements of each type of thing, and all of them on a local cluster and on a remote cluster. So 23 seconds on microcates on my computer on average, 59 seconds on Google Cloud on the cloud on average. So looking at the logs, I noticed that downloading dependencies is what was taking the most time. So let's try not downloading dependencies. Let's vendor things instead. So let me show you what's different here. This is a diff of the previous Docker file and the current Docker file. All I'm doing here is I create a vendor directory. I copy the vendor directory to my image, and then I tell the Go compiler, hey, don't download all of this stuff again. Just use my vendor directory. And that works, and that's going to give us an improvement. Okay, so let's see how long vendoring takes. 13.343 seconds. So on average, 12.4 on a local cluster, 44 seconds on a remote cluster. You can see that we are now taking 52% of the initial time on a remote cluster and 73% of the initial time on a remote cluster. So that's good, that's really good improvement, but we can do better. So what if instead of vendoring, which involves putting all that vendoring cache into the image every time, what if we use an image layer cache? So what does that mean? If you understand how Docker layers work, here first I'm copying all of the stuff I need into my image. Then I'm copying my Go mod, and then I'm downloading all my dependencies. So I have all the dependencies in the image before I even get my code there. And then I get my code there, and then I compile it and I run it. And the point is that I can change my source code. And as long as I don't change my dependencies, it doesn't need to re-download the dependencies. So that is pretty good. That's interesting, because now if I'm not, basically, like I said, if I'm not messing with the dependencies, I don't need to copy dependencies around. They're already cached in Docker. So that can save us a ton of time there. So let's see how that does. And okay, starting again. Let's see how long this is going to take. You can see that my dependencies are cached. And about 10 seconds, I think. 13.9, okay. So 11.9 average on a local cluster, 39.6 average on a remote cluster. When you look at the table now, so you can see that layer caching was a bit faster in both cases, local and remote. But you know what, I'm not going to use it. And the reason I'm not going to use it is, let's say you're writing a Kubernetes operator, and your dependencies are like, API machinery, client Go, all of that stuff, and they're huge dependencies. And every time you change a single dependency, you're going to invalidate the whole dependency layer on the image cache. And what that's going to mean is, if all of your dependencies total 1 gigabyte, you're going to have to download a whole gigabyte. If you're using vendoring as opposed to layer caching, you only change the thing you changed, and the rest is already there. So vendoring takes a tiny bit longer, but you don't have the downside that whenever you change the dependencies, it takes a whole lot longer for that one time. So I like that, so I'm going to stick to that. We're going to stick to vendoring. So if you Google how to optimize my Go binary something, you're going to find 100 billion articles and blog posts saying you should remove debugging artifacts. Now, what are these? If you ever use a debugger like Delve or GDB or anything that you can go step by step, line by line on your code, that's a debugger. For that to work right, you need debugging artifacts present on your binary. Now, that information takes a whole ton of space, which is cool if you're using. But most of the time, we're not using a debugger. Usually, you know when you're going to need a debugger, and then you know when you're not going to need a debugger. I mean, of course, it depends, but generally, I find that to be the rule. So when you're using a debugger, leave that stuff there. But when you're not, which is most of the time for most people, just get rid of it. It's going to make your life, it's going to make your feedback loop faster. So in Go, that's pretty simple. You just tell the compiler, hey, get rid of this trash. I don't want it. So you just put that flag here when you build, and you can see that my binary size went down 3 megabytes, which is very significant. And we're going to see how it's going to get even more significant as we go on. And let's see what happens now that our file size is going to be quite smaller. It's going to do its thing. I should have learned some jokes to tell while it is showing the build time. What's a good joke? Oh well, too late, 12 seconds. Okay, so 10.5 average for a local cluster, 33.9 average for a remote cluster. Now we're taking 44% of the initial time with no debugging and vendoring, and we're taking 56% of the initial time on a remote cluster with no vendoring and no actually with vendoring and with no debugging cache. So, okay, so this is cool. We're gonna just do it by default. All right, moving on. The Go compiler cache. The Go compiler cache is amazing. It is insanely efficient, and you should use it every time if you have a chance to. And right now we're not using it because we're creating a new image every time. So when Go compiles the binary, it creates a cache and it stays in the image. But when we change our source code, we're just throwing that whole stuff away. And creating a new image that comes brand new with no compiler cache. So we're not taking advantage of that, and we should. So let's try and do that. So why should you use a compiler cache? Because without a compiler cache, it takes me 4 seconds to compile the service. With a compiler cache, it takes the blink of an eye, and I like not having to wait all that time. So the way to do it is pretty simple. You just tell Google, hey, there's a Go cache here. If there isn't one, you should create one and just put it there, and then use this cache. So let's see how long this takes. And it's going to be faster, but how much? Okay, 9.41. I think that's the first time that's under 10 seconds, so that's cool. Now, on a local cluster, it took 7.79 on average. On a remote cluster, it took 50 on average. So, all right, we need to have a chat here because those are very discrepant results. The compiler cache is a bunch of very tiny files. And depending on the local cluster you're using even, so like Kind, Microcates, Minikube, they do I/O differently. So copying a ton of files here and there, it's going to take some effort. On Minikube, this actually takes longer to use a compile cache than to not use one because the I/O cost is so high. On Microcates, it was faster to use it. When using a remote cluster, we have that problem again because we need to get all those 100 billion little tiny files of the compiler cache into the cluster, and that takes a toll on the networking time. And then there's a complexity cost. So when I was trying to do this, for some reason, the compiler cache that I was generating on my local machine did not work when I put it inside the image. Could be a version issue, I don't care. But my point is, I had to compile inside the container, extract the cache from the container, and put it on my machine. And then I would create a new version of my code. I would have to take that cache that I copied from a container and put it inside the other container so that it would work. Yeah, okay, anyway, it doesn't matter. Long story short, it's very complicated and flimsy and error prone, so let's not do it like this. Let's find a better way. Okay, now, let's try something different. What if instead of creating a new image every time and putting the compiler cache there, what if I have an image and I never destroy the image? I always have the same image there. Compilation happens inside the image. The compiler cache stays in the image because the image never dies. And what I do is I sync my source code. I sync the source code into the live running container, recompile in place, and then I keep the compiler cache there. Is that going to work? So let's see. So we hot reload the source code, and I could add the title, hot reload the source code into a permanent container. permanent, right? This is a diff where here's the previous version of my tilt file that I showed you in the beginning. There's like the Docker build call, the KTML call, all of the stuff that I talked in the beginning. Now we're gonna add a live update function here, and this is built in on tilt. You don't have to write this function. And I'm just gonna say that whenever something changes in this service, I want you to synchronize the contents of the glitch directory on a local host with the glitch directory inside my container. And something else, I'm going to need a tool that's called enter that's going to watch for changes of Go files. And whenever a Go file changes, it's going to recompile in place without killing the container. So I make a change locally on the source code. That source code gets synchronized with the file system inside the container. Inside the container, I have this application called enter, watching my Go files. Every time it detects a change, it rebuilds and restarts the Go process. Sounds complicated. In practice, it's kind of pretty easy, pretty straightforward. So let's see how long it takes. And oh my God, boom, it's already done. I didn't even have time to sip some water. 2.3. Let's see on average, local cluster 2 seconds, remote cluster 2.5. So my promise at the beginning that we would get down to 2 seconds average, there you go, we have 2 seconds. So there we go, we achieved something. So now you make a change to your code and it takes 2 seconds for it to be up and running on your cluster, and that's great. So let's talk about this. Why is it so much faster? It's so much faster because instead of killing a container, creating a new image, pushing that image to the cluster, and Kubernetes making sure the whole thing is up and running and working, instead of doing all that, all I'm doing is, here's a new source code, recompile it. So it's much more straightforward, especially for the remote cluster, where we're taking now 4% of the initial time. This is huge. This is a huge improvement. But the story does not end here, because we have a problem. And the problem is that here I need all the tooling to build my stuff to be inside my image. And that's going to mean that this image is not going to be the same image that I'm using in production. Because in production, I want basically an image with nothing but a binary. And that image is going to be very tiny and very slim. But that's not the case, because here we need all the Go tooling. So we can improve here. And there's another issue, which I'm going to show you right now. So compiling requires memory and it requires CPU. And sometimes, especially if we have 50 different services on our system, we can't give too much power and memory, too much CPU and memory to each service. They need to be very, very slim. So sometimes compilation is not going to work right. So what if I say that, oh, hey, instead of having a whole processor, I'm going to give it half a processor? Is that going to affect my compilation time? And yes. Locally, it went up to 4 seconds by having half a processor. And here I decided to have 1/10 of a processor, and it went up to 16 seconds. So this is absolutely ridiculous. And my point is, if you don't have all the horsepower for every service, then this might take longer than other approaches. And then you should not use it. But if you do have all the horsepower available, then this is great and you should use it. So yeah, the underpowered version here has worse times all throughout. So let's try something else. Now, what if instead of compiling inside the container, what if let's do half and half here? Like what we're doing right now is we have a container that does not die, and I sync my source code and compile in the container. So what if we have a container that does not die, but I compile locally? And I just sync the binary, and then the container only has a binary, and I compile locally on every code change, compile on my computer, because it's usually powerful enough for that. I sync the binary, it gets restarted in the container. Let's see if that works. So how do we, well, local compile and how to load the binary. So let's see how we did. Oh, yes. Before we see that. So, yeah, if you try to build locally and run in another machine, you're going to have a problem with dynamic libraries. Now, I could go into a big discussion about Alpine and GNU, C library, something. Just trust me, if you're doing this, you want cgo enabled to be 0, and we can have this discussion some other time, but yeah. So here, old version of the tilt file here, new version of the tilt file here. Instead of doing all of this stuff here where I update the timestamp, I'm just using an update.shell file. And here I'm both updating the timestamp and compiling locally, as you can see, with cgo enabled equals 0. Now, this is not best practices. I did this for testing. If you want to do this for Rio, you should do it slightly different. My point is, don't just copy this specific part. Anyway, moving on. Now, instead of syncing all the contents of my source code, I'm simply syncing the binary. And same thing here. Now we don't need the Go tooling anymore. It's just Alpine. It's not Golang Alpine anymore. We're not syncing a directory. We're just syncing a binary. So same thing in two different places. And let's see it in practice. Okay, so we click reload and oh, it's already there. Okay, 2 seconds, cool. So average local, 1.8 seconds, average remote, 9.9 seconds. We need to talk about that average remote. So this is the final, well, not the final tally, but almost the final tally. So if you're using a local cluster, this is the best you can do. This is what you should do every time. I haven't found some time when you should use any of the other approaches if you're using a local cluster. If you're using a remote cluster though, here's the thing. Now, before you were copying a few kilobytes of source code. Now you were copying a big Go binary, and Go binaries can be quite big, so that's why it took longer here. So I'm going to show you one more thing that you can do. You can use a thing called UPX, that's the Ultimate Packer for eXecutables. So if you think that executables can't be compressed because they're optimized out of the compiler, blah, 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 transmitting things in the network, you compress the packets, blah, 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 no, you're wrong, you can't compress it. So you can use this tool called UPX, and it can reduce sizes of binaries significantly. And let's see how it works. And it's going to make a big difference for when using a remote cluster. So if we scroll up here, it took 3.8 seconds. If we go up, come on, yes, you can see that now we are only taking 40% of the original size of the binary. So when using a remote cluster, it went down to 6 seconds. And when we look at the final table, all right, so now that we have all these numbers, let me give you the rundown of the final results. So if you have a lot of processing power on your cluster and you're using a remote cluster, this is the fastest time you're going to get. You should hot reload your source code and compile inside the container. Now, if you don't have a lot of horsepower available, or if you don't want your development and production images to be different, then you should use, you should build locally on your development machine and sync the binary into the container. In that case, you're probably going to want to use UPX to reduce the binary size and make it faster, but that depends on your network. If you have a very fast internet, you might not need to do this. Let's say you have a lot of processing power and very crappy internet connection, then you might want to crank UPX up so that it zips things even more. So that trade-off is up to you. If you're using a remote cluster, then there's no discussion. Building locally and syncing that into the cluster is the fastest. And we can argue about this, but I have never seen a better approach. If you have, please show me. And just as a note, if you're using a dynamic language like Node or Python, you should just use this approach. Just hot reload the source code and restart it there. And that's basically all you need to do, and you don't need to think about this. There are some concerns about other languages. So some languages, they are compiled and they produce tiny binaries, but maybe they're cross-platform or not. So that's a separate discussion. I think this data as it is should help you a lot in your workflow right now. So how do you learn further about this? We did not talk about Scratch containers, and that's something that we could play a lot with. So I did not do that. If you want to do this exploration, please show me the results later. And when I talked about CGO and dynamic linking before, I didn't explain it much. If you want to learn about that, or if you want to learn more about reducing image size, check out this article by Jerome Petazzonis. It's really worth reading, and it goes on about other languages too, and I highly recommend it. So I hope this was useful to you. I hope you learned a thing or two here. If you want to learn more about Tilt, please reach out to me if you want to just chat about the subject. So I hope this was fun to you, and see you next time. Bye.